We're now moving on to the second chapter that we're going to cover within the Year 13 Pure Maths textbook, and that's chapter 9, which is all about differentiation. So we've got quite a lot to cover over a number of lessons within this chapter. But the first thing we're going to have a look at is how to differentiate some trig functions. So we're going to look at differentiating sinx and cosx. But before we go on to that, we're just going to have Okay, so this is our little warm-up question. So what I'd like you to do is just to pause the video, write down the question, and then have a go at that question. Okay, take you about 10 minutes or so. So have a go. Once you've had a go, then start the video again. Okay, if you remember from the previous lesson that we were doing, we had some small angle approximations. Now the approximations were, if you had sine theta, that was approximately equal to theta. Tan theta was also approximately equal to theta, but cos theta, a little bit more complicated, was approximately equal to 1 minus theta squared over 2. Now don't worry, you don't need to learn these. They are on page 5 of your formula book, so just make sure that you know where they are in the formula book. Now it is a show that. Okay, so I'm going to have to show nice and clearly what I'm doing in each step. So I'm going to take this equation here. Okay, and I'm going to put in my small angle approximations. Now cos theta is approximately equal to 1 minus theta squared over 2. So when I've got cos 5 theta, remember the theta is replaced by 5 theta, but I need to put it in a bracket because it's all squared, including the 5, plus 203, again tan 10 theta, because I'm using this one, tan 10 theta approximately equal to 10 theta. Okay, equals 182. I'm going to expand out my bracket here. So 32 minus, use your calculator to help you there, 32 times 5 squared divided by 2 gives me 400 theta squared. Okay, and then this gives me 2030 theta equals 182. Have a look at the thing you're trying to prove up here. They've put all of it on one side with a positive amount of theta squared. So I'm going to move everything over to the right hand side. So I get 400 theta squared minus 2030 theta. And then 182 minus 32 gives me 150. And you can see I'm almost there because the thing I'm trying to prove, all I do is then divide everything by 10 to get that. So that's the kind of level of detail. It is worth 4 marks, so that's the sort of level of detail that the examiner would expect to see. Okay, part B says hence. Okay, so we must use what we've done in part A, which we're obviously going to do. You can see that the solutions of that equation, because of what we showed in part A, are equivalent to solving this equation, 40 theta squared minus 203 theta plus 15 equals 0. Now I would put that into my calculator, okay, just to see what sort of solutions I get, and it does actually factorise if you look at your answers in your calculator. So work backwards from your answers that you got in your calculator to show the factorising. One of the answers was theta is 5, and one of the answers was theta is 3 over 40, so that gives me the other bracket, 40 theta minus 3. So do show this, because it's 3 marks here, do show the factorising. Despite you using your calculator to help you factorise, do show the factorising, and that gives me theta equals 5 and theta equals 3 over 4. Okay, those answers are radians, so let's put my little C. Now part C is only 1 mark. Comment on the validity of your solutions. Now what's important here is for this part A, this part here, theta is small. Okay, so we've got 2 answers here. Theta is 3/4 radian. Now that is a small value, so it's going to be valid for that. Theta equals 5 radians. 5 is a big value. Okay, so it's not going to be valid for that. So what we'll say is valid for theta equals 3/4 radians. It's small, okay, but not valid for theta equals 5. Okay, that is too big. And what you'll find is if you do actually sub that back into the equation, you'll find that if you put theta as 3/4, then you pretty much do get that. Okay, if you put in theta as 5, you'll be, quite away from that. Remember when we looked at the graphs for the small angle approximations, it needs to be for small values of theta. So if you weren't sure of a part C, you could always pop them back in and see which one works and which one doesn't. Okay, so hopefully you'll fine with that. So this is all of the things we need to do for this chapter. It's going to cover a number of lessons, some of which will be before the summer holidays and some of which will be after the summer holidays. So what we're looking at today is just differentiating sinx and cosx. Okay, quick recap then. You have done some differentiation. So again, pause this and have a go at those. Do remember your notation though. Y equals that. If you differentiate, you write dy dx equals. Okay, don't just write equals or y equals, you write dy dx equals. Okay, so have a go at those. Right, for your differentiation, what you should have been saying to yourself is bring down the power, reduce the power by 1. So if I differentiate that, I get 9x squared plus 5. Okay, so to differentiate the second one, at the moment we can't differentiate a product of functions, but in a few lessons time we will be able to differentiate a product of functions. So at the moment the only method you can use for that is to first expand out your brackets. So expand out your brackets carefully. 10x to the 4 minus 23x squared minus 5. Okay. So that's minus 25 plus 2. So again, notation, write dy dx equals, bring down the power, reduce the power by 1, bring down the power, reduce the power by 1. Okay, this final one then, again, bring down the power, reduce the power by 1 is all about indices. So what you want to do first is you want to write these as x to the power something. Let's see if you remembered this one, which can be a little bit of a trick. This is equivalent to this. It is not equivalent to 2x to the minus 1. The 2 stays on the bottom. Remember that. Examiners love those ones because they're easy ones to make a mistake with. So remember, when you've got 1 over, it's a negative power. Once I've written them like that, plain sailing, because all I'm going to do is bring down the power, leave the half the same, reduce the power by 1, x to the minus 2. Again, bring down the power, so I've got minus 4 times minus 3, which gives me plus 12, reduce the power by 1. Okay, so you're happy with those? That's to do with polynomials or powers of x. Let's go on and have a look at sin x and cos x then. So before we determine what the differentials are, we need to remind ourselves of something. Now, this wasn't something that the mechanics teacher did with you. This was done by the stats teacher when you were doing differentiation, and it was differentiation from first principles. So this is really just a reminder of what it's all about. It's all about having 2 points. Okay, remember, differentiation is all about finding the gradient function, the gradient at a point. So what you have on a curve, if you have 2 points that are a distance h apart, then what you do is you say, well, the gradient of the straight line joining those 2 points is given by this. And then you do the limit of that as h tends to 0, which will then give you the gradient at a point, because as b gets closer and closer to a, okay, so as this goes down closer and closer to A, you will then end up with the gradient at the point A. So you end up with this, okay, as your definition of the derivative of a function f of x from first principles. Now, don't worry about learning this, because this is on page 2 of your formula book. So grab your formula book, go and have a look and find it, because if you are asked to differentiate from first principles, this is what you'll make use of. So you must make sure in your formula book, page 2, okay, just grabbed mine, it's just on that very first page and it says differentiation first principles, and it gives you this here. Okay, So this is what we're going to make use of to find the derivatives of sin x and cos x. So hold that thought. We're also going to make use of these. Okay, we've had a look at these in our little starter already. Again, don't worry about learning them because they're on page 5 of the formula book. So while you've got your formula book open, just have a look and you can find them. Oh no, page 6. Go and find them on page 6 of your formula book. Okay, you'll see them there. Right, now the reason we're going to make use of these is, okay, when we're looking at sin x, because we're going to be differentiating sin x, remember sin x is approximately equal to x and cos x is approximately equal to 1 minus a half x squared. Okay, so that's our small angle approximations, but just with x, theta replaced by x. Now remember, for these to be valid, we do need to have x in radians. So that tells you that when we're differentiating sine and cos, or anything to do with trig functions, we need to be in radians. Now, the reason we're going to make use of these is because that tells you then that if I do the limit as h tends to 0 of sin x over h, sin h over h, I get 1, okay? And also, if I do the limit as h tends to 0 of this thing here, which you might think, why am I doing that? But just we'll have a look in a minute. That is equal to 0. Okay, now it says on here, learn this information. I have seen in exam questions when they've asked you to prove from first principles that they've given you this information, okay, but you should have it to hand just in case you'll need to make use of that. Okay, right, so one more thing we use in this proof from first principles is these addition formulae. Okay, so the addition formulae, again, oh, I've got that page 5, page 6. Okay, page 6 of the formula book. All right, I've got my 5s and 6s mixed up. So just above the small angle approximations, and they look like this, called addition formulae. Okay, now make sure you know how to read these because they're given in the formula book, but they're given like this. Can you see here? We've got a plus or minus on top of each other, and here we've got a plus or minus on top of each other. So what that tells you, this is two formulae in one. So if I read the top line, sin A plus B is sin A cos B plus cos A sin B. And if I read the bottom line, sin A minus B is sin A cos B minus cos A sin B. Compare that to the cos one. If I read the top row for this, cos A plus B is cos A cos B minus sin A sin B. Okay, you can see how they work. It's two formulae in one. You read the sign either from the top row to give you one of them or the bottom row to give you the other one. Page 6 of the formula book. Go and find them. Make sure you can see them. They're right at the top. You'll do more work on these later on in year 13. Okay, you'll get more familiar for them. Right, familiar with them. Okay, let's do our proof then. Okay, so we are going to prove from first principles that the derivative of sin x is cos x. Okay, now this can be you could be asked to do this in an exam, all right, and it's worth about 5 marks, something like that. So you must make sure that you remember what we've done for this. So what I'm going to do, so I can make use of the first principles formula that's in the formula book, I'm going to say let f of x equals sin x. Okay, because that's the thing I'm differentiating. Now, from my page 2 of the formula book, and I'm allowed to use this, the derivative is the limit as h tends to 0 of f of x plus h minus f of x over h. Okay, so I've just copied that from page 2 of my formula book. Okay, so now I need to replace the f of x plus h from my definition and the f of x from my definition. So that's equal to the limit as h tends to 0. Now f of x plus h, remember from your functions work, that is sine of x plus h. Okay, so it's the sine function but with the argument replaced by x plus h, that's minus sine x all over h. Here is where we are going to use our addition formulae So the addition formulae is going to be used for this bit here. So let's look at our addition formulae. Our addition formulae says that's equal to sine x cos h plus cos x sine h. Make sure you're happy with that. Okay, I've still got my minus sine x all over h. Okay, now here's the bit that you sort of kind of need to remember that you have to do this, is we now are going to do a bit of factorising. So what I'm going to do is I'm going to gather together the terms that have sine x in them, and what you will find if you have sine x times cos h minus 1 all over h, okay, and then plus cos x, so take out the bits with x's in, basically try and remember that, cos x times sine h over h. So this is where I'm making use of the thing I was talking about before, where we used our small angle approximations. This bit here, okay, this tends to 0 as h tends to 0. Remember, because we put in the small angle approximation and we showed that that tends to 0, and this tends to 1 as h tends to 0. So as h tends to 0, what we end up with, this bit, whole bit here, okay, becomes sine x times 0, and then this bit here becomes 1 times cos x, so that is equal to cos x. Okay, so what that tells us is the derivative of sine x is cos x. Okay, so that's the kind of proof that you would need to state. If these bits here, okay, are not given to you in the proof, then you may well need to sub in the small angle approximations for this. So remember, this is approximately equal to h, so you get h over h, which gives you 1. And you may need to sub in the small angle approximation for this. Do you remember that's 1 minus h squared over 2, and then you've got the extra minus 1, so you end up with minus h squared over 2 over h, or minus h over 2, which tends to 0. Okay, so if you do need to put that bit in and it's not given to you, then please do. Okay, right, so sine x differentiates to cos x. Okay. The other one we need to do is cos x goes to minus sine x. So what I would like you to all do is write that down, prove from first principles that the derivative of cos x is minus sine x, and then pause this and have a go. You are doing exactly the same as what we did in the previous one, okay, except you are starting with f of x equals cos x, okay, and then you're going to use the definition of the derivative from first principles from the formula book. I now know it's page 6, not page 5. And then you're going to sub into that. Okay, so pause it and you do it. Right, let's, oh, I've lost my limit. Okay. Okay, so now let's sub in my function. So I've got cos x plus h minus cos x over h. Addition formulae. Remember when you're reading the cos one, I always remember the cos one goes cos, cos, minus, it's got the opposite sign to what's in here, cos, cos, minus sine, sine. Okay. Oh, sorry, that's a little bit of factorising. So this time take out the cos x and I get cos h minus 1 over h, and then take out the sine x and I get sine h over h. Same as before, this tends to 0 as h tends to 0. This tends to 1 as h tends to 1. So what do we end up with? Minus sin x. Okay, so the derivative of cos x is minus sin x. So sin differentiates to cos, cos differentiates to minus sin. Okay, so hopefully you got there with that. You do need to be able to reproduce those because you may be asked to in the exam. Here's a summary. Okay, so if y equals sin x dy dx is cos x, if y equals cos x dy dx is minus sin x, there are given to you in the formula book some more complicated derivatives, but these are not given to you, so you have to remember these, you have to learn them. And this is important. Remember why this is important? Because we're making use of those small angle approximations and we can't use those, okay, unless x is in radians. All right, good. Okay, now there are also some slightly more complicated expressions in sin x and cos x that we need to differentiate, okay, and they are if y is equal to sine of, say, 3x or something like that, then when you differentiate you get cos of 3x, but you would times by the 3 at the front, or you times at the front by the differential of the argument there. The same with cos, okay, and remember x must be in radians. Now here's the important bit to remember with these. If y is sine of kx, notice in my differential, sine goes to cos, but you must not change the argument. So this is the same argument, okay? Again, with this one, cos of kx, you get minus sine, but you get minus sine of kx. So same argument. You must remember this. That is such a common mistake that people make, okay? Right, we're ready to do a couple of examples now. So here's our first example, okay? So find dy dx given that ay equals sine 2x. Okay, so if y equals sine 2x, use the right notation please. Dy dx is equal to, sine goes to cos, but because I've got a 2, I get a 2 at the beginning, cos, remember it's 2x, so the argument doesn't change. Part B, cos 5x, dy dx equals, you're going to get the 5 at the beginning because of the 5x, cos goes to minus sine, put my minus at the beginning, okay, so you get minus 5 sine, again, look here, 5x, 5x, 5x. Part C, you know with differentiation, if I've got functions made up of things added together, I simply differentiate each term separately and add them together. 3 cos x, cos goes to minus sine, so I get minus 3 sin x. Okay, plus sine goes to cos, okay, but because I've got the 4 here, I'll get 4 times it. I've already got a 2, so I get 8 cos 4x. Make sure the arguments here, and here stay the same. That's the important bit. Now let's think of the applications of differentiation that we've done before. You can find stationary points, you can find maximum, minimum, you can also find equations of tangents and normals. All of those can be done with trig functions, so you'll see the questions you're going to be doing in a moment. There will be finding equations of tangents and normals, there will be finding stationary points as well as just simple differentiation. Make sure you remember, okay, with your tangents and normals, when you differentiate, you get the gradient of the tangent at a point. If you want the gradient of the normal, negative reciprocal. Okay, so one more example, we're going to just find some stationary points. Now, the question gives you a little hint, okay, but you must make sure that x is in radians. You must make sure anything to do with differentiation or integration. So stationary points, that should tell me that I'm going to differentiate my function My function here is made up of 2 bits. There's a bit involving x, so when I differentiate half x, I just get a half. There's a bit involving minus cos 2x. Cos goes to minus sign, so I get minus sine 2x, but remember, because of the 2, I get a 2 at the beginning. Okay, so that differentiates to that. Gradient function 0 for stationary points. Okay, so I'm basically solving this equation. So what do I get? I'm solving sine 2x equals minus, I'm going to take the half over, divide by 2, minus 1/4. So we're now into the realms of solving trig equations again, like we were a couple of lessons ago. So 2x equals arcsine minus 1/4. Pop that in your calculator and it will say minus 0.25268 radians. Make sure you're in radians, okay? We want our x to be in this interval here, okay? So that's not actually a valid answer. So before I do my divide by 2 to get values of x, I must use my cast diagram to get the values I'm interested in. So the one it's given me is here, okay, because sine is negative in this quadrant. Where else is sine negative in this quadrant? Now the values I want are all going to be positive, so how I'm going to read them off, the first one I'm going to start here at 0 and I'm going to read right the way round to that one. Okay, remember that's your 0 there. So that one is 2x equals, remember the value of this is 0.25268, as is this one here. So 2x is equal to pi plus 0.25268, okay, which is 3.39427. I'm keeping quite a few significant figures here and then I will round it at the end, okay. I've also got, if I do it in a different colour just so you can see, I've also got the other one to read off is all the way round to here to give me the positive value. So that is 2x equals 2 pi minus 0.25268, and that is 6.0305. So it's now only at this stage that I do my divide by 2. Okay, so for my first one here, x is equal to my 3.39427 over 2, which is 1.697. Okay, and then for my second one here, x is equal to 6.0305 divided by 2, which is equal to 3.01525. Now here's the bit where make sure that you are aware of what it's asking you for. It's asking you for station points. Okay, so it's expecting you to give coordinates. So this is my value of x, so I sub back into my equation to get y. So I'm going to show my subbing in, half times 1.697 minus cos of 2 times 1.697. Okay, in radians, 1.8167. So I'm going to give my answer as coordinates, and here I'm going to round to 3 significant figures. No accuracy is specified, so 3 significant figures is always a good level of accuracy if nothing is asked for. Let's do the second one. Y equals a half times 3.01525 minus cos of 2 times 3.01 dot dot. Run out of room a little bit there. Pop that in your calculator, 0.53938. So again, let's specify my coordinates to 3 significant figures, 3.02 and 0.539. Okay, and because I've got a 180 or a sort of, between 0 and pi, I'm expecting to get 2 answers because I've got a cos 2x here. So that's the right number of answers. Any more would go outside of my range. So make sure, stationary points, make sure you give coordinates for them in radians. Okay, well, x will be radians, but y won't be. So make sure you give 3 significant figures unless other accuracy is specified. Make sure you remember how to do equations of tangents and normals. Okay, what you would do is differentiate. So here's my gradient function here. And if you want the equation of a tangent at a certain point, you put in that value of x to get the gradient at that point. If you want the normal, remember the normal is the negative reciprocal of that. Okay, over to you then. Exercise 9a, remember in your Year 2 textbook. Questions 2 to 9, all of those, write out the question. Okay, it's a couple of pages of work. Use your correct notation, so write either dy dx, or if you've got f of x, so it's either dy dx, or if you've got f of x, it's f dash x. Okay, show your clear working, x in radians. Don't want to see any of those submitted, and we'll go through that in our Teams lesson next week. Okay, thank you very much and good luck with those.